Hello, everybody. Hope you're having a great day. This is Mason Avaran. I've been with Ozone Engineering for a year and a half, roughly. Before that, I was with an electric car company called Byton, and before that, I was 5 years with Ford Motor Company. The YouTube short we have today is about Turbomachinery. This is the second YouTube short we have. A little bit about us. We have been in the Bay Area for 17 plus years and successful operation during that time. We have 1,000 plus happy clients, and we are the elite channel partner of ANSYS. We have a lot of expertise in multiphysics, finite element analysis. Also, we have expertise on computational fluid dynamics or CFD and electromagnetics, which includes both high and low frequency. Our territory includes Oregon, Nevada, and California. We have headquarters in Sunnyvale, and also we have offices in Portland, Oregon, and also staff in Long Beach, California. Here is the list of software that we can sell to you. These are including in different categories. In structures, you have mechanical, Palestina, Encode, and a lot more. On fluids, you have Fluent, CFX, FenSap, Forte, TurboGrid, and you name it, a lot more. On electromagnetics, we have two categories, high and low frequency. High frequency mostly includes HFSS, SI Wave, and on low frequency, we have Maxwell, ARM Expert, even MotoCAD. We have some semiconductor tools as well, and also optics, which includes Optis. On material side, you have Granta, our embedded software. We have different packages of Skate, and for system, we have TwinBuilder and Medini. So whatever industry you're in, don't hesitate to give us a call. We can definitely give you the right tool and make your product development process faster and more efficient. In the previous YouTube short, I focused mostly on the introduction and applications of the turbomachinery in different categories and how you break it down. But in this YouTube short, mostly I'll focus on CF Turbo, and we'll do an example problem on fan initial design or conceptual design. First, I'll go to a couple of slides to see how it looks like, and then I'll go step by step in the actual tool. For fans, as you see, when you open the CF Turbo tool, you have all the options, which includes pump, fan, compressor, and turbine. If you choose, for example, fan, based on that, you have minimal amount of data, let's say like flow rate, pressure rise, and RPM, which is usually the limit because of the structural durability. And just by having this minimal amount of data, you would be able to find out what kind of turbomachinery is recommended for those operating conditions. You need to take some steps for the design to happen. First, you need to define the main dimensions, which is mostly based on the best efficiency points. Then you do the meridional contours, which is like a side 2D, I would say, plot of the turbo machine. And after that, you design your blade properties. You define blade numbers, their shape, their angle, their type, etc. And you have a lot more things to tweak. After that, you do the blade profiles to define the thickness, and even if they have a certain profile, they can be modeled that way. And finally, you do something named as blade sweep, which is a little tweak in the final design, which is mostly done for NVH or acoustic purposes. Here's a sample problem. As you see, we started with an impeller or rotor, which is the blue part, and then at the end, we added a stator downstream of that. And here is just 3D geometry based on that, from which you can start more accurate and higher fidelity simulations, such as FEA or CFD. From now on, I'll go to the actual tool. Here is the problem that we'll be doing for today. I'll close it totally and start from the scratch. So when you open CF Turbo, you have these options. As I mentioned, if you're looking to design an actual fan, something similar to what people use in cars, data center cooling systems, or let's say, I would say drones. You define the operating conditions. Let's say you want to have 3000 cubic meter per hour is a flow rate you have in mind. You want to increase the pressure by 500 Pascal, and the limit for RPM because of durability is 3500. You can choose different materials or fluids. You can even enter some custom materials, but here air, I think it's a good estimation. It's just a cooling fan, let's say for electronics on an airplane. As you see, the purple triangle moves right and left based on the operating condition. Let's say, for example, as you see, so it commands that for these operating conditions, it should be in the rate in the sorry actual range. So you'll have a fan that would be mostly an actual fan. So we go to next step, and also you have the Cordia diagram. You're in the green region, which means you're optimally located. There's a lot of empirical data inside that recommends the best operating condition for better efficiency. Here you have to choose the actual impeller, or I would say the rotor. That's where you start with. This is what you have. You have a unshrouded one. Let's say for simplicity, imagine you have 1 millimeter clearance between that and the casing. Everything is used as default. You have a standard and it has an airfoil for parameter. Also, you have some non-dimensional numbers such as a work coefficient or diameter ratio that you need to define. But here, the good thing is that it automatically calculates that for you. So there's a lot of empirical data based on that. It tells you that the work coefficient should be in the gray area and you're almost there. So if you change it, it even tells you how it would change it. Let's see if you make it a little higher, you'll be this much off from the optimal point. I'll put it back to automatic. So because I like the empirical data that it has inside. And this is a good point for efficiency, I would say. Information is quite the default values. I don't change it. And this is the meridian or the side view, and Cordier, and also the velocity vectors. At the end, it gives you even some recommended values for the hop diameter. To make it just straight numbers, I just make it, let's say, 1111 and 272. Similarly for the outlet, just for feasibility and simplicity and convenience in manufacturing. The next step is, as you have at the bottom left, you have all these steps that should go one by one until it's completed. Then I go to the next step, which is the meridional contour. Here's the contour as you see here. This is the blades. This is like a side view. You can have any profile for the blades. Let's say I want to assume that the leading edge is a straight line and trailing edge is like Bezier curve or like a smooth curve. I can even do that for the leading edge. You can do it as you want. And then after that, I should define the hop. I check it and I say, okay, how should my hop look like? Let's give it a thickness. Let's say it goes all the way up to 28 mm. Just make sure it's accurate enough. Here it goes all the way till 20. I think it should be good to go. And this is secondary flow path. I don't think you need to worry about it. That's where you have some leakage from your device, which is not going to be discussed in this YouTube short. The next one will be defining the blades, but just let's see, just for the sake of it, how it looks like so far. If I click OK, if I go to 3D model, you see I have the hub and I have the outer layer of the casing, and then you need to put the blades on it. So, okay. The next one was defining the blades. Go to blade properties. Here's what you have. You can set the number of blades and even like how many spans you're going to have. For example, for one blade, you see here, you have 15 spans. If you make it smaller, it will be less kind of number cross section or pixels in the normal directions, as you see. And then here is the how to shroud velocity profile. So let's make this, I mean, you have a lot of options you can play around with to get the profile you're interested in. I'll make it something like this. Okay, and then after that, the profile selection. I think you have everything, the angles, the curves, velocity vectors. And you go to profile section. You have for profile section different options you can choose. There are a lot of NICA profiles that are available. You can choose. I'll stick with what I have so far. And then after that, you go to also other thing, which is the profile properties. This is we go with the angles that we have in mind. It can be calculated even automatically. You don't need to worry about it. And we should be good to go. So we go to next step, which is again, the blades kind of thickness and the more details on it, which is the next tab. This is a blade profile. As you see here, this is the blade profile, how they call it twisted blade profile. You see how it looks like. You can see even the thickness, it goes up and comes down. It's a little exaggerated. And then you can see even some 3D view of it too. See, we have this blade shape and also the angles. I'm not gonna have too many windows here so you can easily see it. See, that's how it would look like. On the fly, you can change it, and based on that, this would change and you'll be able to see how it would look like. And the other one would be, I would say, the next tab, which is something called sweeping. This is just used for mostly actual fans, but you can use it for other options too. The thing is that you slightly tweak your profile. When you do that, it will let you, let me get rid of some of this so you're more comfortable with it. It's a very small change, but what it does that with that slight tweak, you wouldn't usually change the aerodynamic properties that much, but it just improve the NVH or acoustic properties. As you see, it's very small, it's just a minor tweak. And I think after this, we should be all set. We all finished, so just push OK. Let's see how the 3D looks like. And this is your 3D shape. I mean, even if you like, you can go to that and do even maybe other steps, which is preparing that for CFD, or even you do model finishing, for example. I can do solid trimming, so it gives me a nice clean CAD that I can do anything I want with it. See, with a CAD like this, it's quite a clean CAD. You can send it even to other tools. You can go here, export it to, let's say, as a step, STL, space claim, anything you want. You have all these capabilities. But for now, let's forget about it. Okay, and after that, we need to design the stator. So for the stator, you go downstream side, you say new stator. Let's say we want to have it to be extended almost 120 millimeter. We enter it. And after that, we need to have also blades. So you say you wanted width blades. And then you click on the same type of tabs. These are pretty much similar to what you had for the rotor or impeller, a little different, but I would say similarly, you got to go step by step from left to right until you're finished and you hit the green button for completing. The next step is that you see this is the meridian contour. Do a straight line. Let's say for leading edge, we assume it's to be just a straight line. For trailing edge, I want to have it as a little Bezier curve. I think we should be good. Then we go to the hop design. Similarly, to 20 millimeter radius. Okay, it's all good. Okay, so you're done with one more tab. The second one is the blade design, or the blade properties. So you see, okay, it says how many blades you recommend. I mean, based on the impeller, it kind of gives you some recommendations. Let's say I want to have maybe 10. It tells you if it's good or bad. Doesn't have anything. Oh, not 200. I made a mistake, I guess. Something went wrong. Let's say okay. So we have, let's say, 10 blades. Let's see. It says it's orange. It's too much. It's not recommended, I guess. It's too many. Let's just change it a little bit. Make it maybe 5. Okay, I think it's allowed. It's good. We can go with this. Then you have a lot of options for type of blade you're interested in, but I would keep it simple. Let's say even the thickness is just simple, 3, like a straight number. And everything else is the default. Vectors, meridian plot. Let's make it a little more fine. That's better. This is good. And I think it's all good. Then you go to the blade angles. The blade angles, they could be what it is. It sounds like a reasonable number. And I think we should be good. We go to the next step, which is the blade mean lines. This is gonna define how the curve is gonna look like. It's very aggressive here, the angle, but you can play around with it. You see, these are the blade mean lines. You can define what you're looking for. It's not the best angle. I think it's very aggressive properly. With very aggressive probably you can change it, but just to show you how it is being designed. I mean, you can change with all the parameters to make the angle the way you want, or give the curve the way you want. It definitely needs tweaking, but that's mostly when you're designing a turbo machine, you have to deal with it. Then you go to the next tab, which is the thickness of the blade. For the sake of simplicity, I mean, we just keep it as uniform, but you can put even profiles on it, airfoils on it. Then you go to the leading and trailing edge. You want to have it simple. You want to have it elliptical or a smooth bezier or linear. I would just keep it elliptical, which is a default. And then I think you're all done. All the buttons have been checked. So you just say check. And if you go to the 3D, here is the 3D CAD that we have for it. There is a rotor and there's a stator. This one is rotating and this one is staying. You can even animate it. This is the impeller, this is the stator. Thank you guys for your attention. And if you have any more questions, I'll be happy to answer. Have a great day. Bye.